All right, let's get started. So anybody have questions off the top before we jump into inheritance with comparators? Let's do it. You've seen comparators in 115 potentially. I think they're stopping that this semester. But anyway, whether you've seen comparators or not, if you didn't take 115 here, you might not have seen them at all. Let's talk about them. So even if you haven't heard of comparators yet, I want to do some review / introduction to comparators. So let's talk about what these things even are. Comparator is going to be essentially a method. We're going to wrap it in a class and use inheritance and everything. But it's effectively a method that's going to compare two values and tell us something about the relative order between those two values. So with those two values, how should they be ordered? And we want to use these comparators to sort any number of values. We're eventually going to sort using comparators that compare two values and use them to sort any number of values. We're going to do that with comparators. And there are two flavors of comparators. The first one that I'll talk about a bit is the one that Java uses internally, Java sorting methods, and anytime Java compares, it'll use this first method. And in class, we're going to use this second method, returning a Boolean. But there are multiple methods. I'll talk about the other one for a few slides here, and then we'll shift into just talking about the one that returns a Boolean. But this one is perfectly valid. You might even want to use Java comparators in your homework assignments. So it's important to know how both of these work. And this is the way JavaScript used them. If you remember JavaScript comparators in 115, this is exactly the same thing. But the way this works is our first flavor of comparator is going to return an int. So we ask the comparator, does this value come before this value? So we'll compare, let's call them A and B. Does A come before B? The int comparator is going to return a negative value if A comes before B, a positive value if B comes before A, and 0 if the order is tied, if those values should be, if their relative ordering doesn't matter in a fully sorted order. So this would be like if I'm sorting ints, the ints are the same value, of course. Or if we're comparing strings, one thing you have to do in task 4 is compare strings while ignoring case. So ignoring all the capitalization, as long as it's the same letters, that don't have to necessarily be the same characters, then we'll call them the same. So if we have one that's all lowercase and one that's all uppercase, but it's all the same letters, that would still be tied in fully sorted order if we're ignoring case in our sorting. Our Boolean flavor is going to return true if A comes before B and false otherwise, including ties. So let's talk about the first flavor for a little bit. If you use compare to, like the string class in Java has a compare to method. If you use compare to, it's going to follow this flavor of negative int, positive int, and 0. There's also, I dropped a hint in the homework document itself for homework 4, that compare to, the string class also has compare to ignore case. Might be really, really useful in task 4 when you have to compare strings while ignoring their case. You'll get two array lists. You'll have to compare two array lists, step through their values index by index, and compare each pair of values while ignoring case. Compare to ignore case does half of the work for you. So I dropped that hint right in the homework. No surprises with that one. But let's talk about what compare to and compare to ignore case is going to return. I have these two strings, 1 and 2, A and B, and I want to say compare, hey comparator, does this value come before this value? And this comparator is still taking two values, but one of them is the calling object. So compare to will have a reference to this object through the keyword this. And then the second value is going to be the one that's given as an argument. We're still just comparing two things, but we are taking advantage of references to get there. So does this value come before this value? Does A come before B? It does. So the comparator is going to return negative integer. I almost said -1. It'll return a negative integer. Does A come before A? their order is tied, return 0. Does B, bless you, does B come before A? It does not. It does not. I know the alphabet. So return a positive int. A lot of times, by convention, these comparators will return 1, -1, and 0 as their return values, but they don't have to. In your code, don't ever, when you're using a comparator like this, don't say does compare to equal -1 or equal 1. That's convention. You know, a lot of times we'll use those values, but it's by no means required. If somebody wants to return -99 and positive 1002, they have that right, and it's still going to satisfy the interface of a comparator. So don't rely on them returning -1 and 1. You should always be checking in your tests or in your code, anywhere you're using a comparator, less than 0, greater than 0, equal to 0. Those should be the 3 comparisons. For strings and really any non-integer type, it's common to see -1 and 1. But if I'm comparing 2 integers, say I want to compare 2 integers with the less than operator, and I'm writing my compare to method, and I want to compare 2 integers in variables A and B, I might just return, and I always have to think about this one. I would return A minus B, and that would be my whole comparator. If A comes before B, that value is going to be negative. If B comes before A, that value is going to be positive. And if they're the same, it's going to be 0. So I'm satisfying the condition of a comparator, but I'm not returning 1, -1, and 0. I'm returning whatever values happen to be based on that difference of those 2 values. Yeah?
So like in C++, I remember this, does Java also compare Unicode characters, just subtract that if it's bigger?
Mm-hmm. Yeah, it'll compare them by their, actually, it's my next slide. It'll compare them by their Unicode values. Yeah. I'm not going to go that deep into it in this slide, but yeah, it will be. So when we're comparing strings, they'll be compared, I wrote on the slide alphabetically, it's lexigraphically, it's slightly, there are just a few caveats here. One is if the strings are different lengths, whatever string is well, first it's alphabetically, like if one starts with A and one starts with B, the one that starts with A is coming first. So I think we can all agree on that. But then there are some edge cases that come up. What if one string is a prefix of another one? The one that's a prefix comes before the one with extra characters. And the big one that makes a big difference is every single uppercase letter comes before every single lowercase letter. And this is based on what was mentioned. Their Unicode values, and at this point, even their just ASCII values are sorted in that way. Their ASCII values, in this case, are the same as their Unicode values. But all the uppercase letters come before all the lowercase letters in ASCII and Unicode. So therefore, every uppercase letter comes before every lowercase letter. Say you're sorting songs by title, and all of your songs have proper capitalization. The first letter is a capital letter in all these songs, except one song starts with a lowercase a. Well, that song, and you're sorting by titles, that song is going to be at the end of your list, no matter what. It's going to come after all the ones that start with a capital letter, which makes it common to want to ignore case when we're comparing strings, which is why it's on your homework. Comparing strings while ignoring case. If I have the right characters there, I want to call it the same string in most cases. And if I'm sorting strings, I don't want all the strings that start with uppercase letters and then all the strings that start with lowercase letters. Doesn't quite, it's often not the ordering that you want. Okay, so that's the comparator that returns an int. If you're using, so when we're calling compare to ignores case, which you should do in your homework, don't write your own string comparator method, that's crazy. But you have to write your own string comparator class and then call compare to ignore case inside that class. That's the intended thing. The one we're going to focus on is the one that returns a Boolean. So our comparator is going to return a Boolean, give it 2 values. If the first value comes before the second one, strictly before the second one, return true. Otherwise, return false. And this seems less powerful on the surface. Like we can't do as much as we can do with the int comparator. Namely, we can't tell if the values are tied, but we actually can. So it's a little bit hidden here, but we have just as much power with this comparator as we do with the int comparator, unless we're actually checking the values of the ints if we want those to have meaning, I guess. But here we have just as much power. If I want to know if the values are tied, I want to say, does A come before B? If it says true, I know A comes before B, and I get all my information. If it returns false, I don't know if B comes before A or if it's a tie. So how do I reconcile this? How do I figure out if it's a tie? Sure, you could say it. Flip it around. Yep. Call the comparator again with B comma A. If that returns true, B comes strictly before A. If that returns false, it's a tie. So if I called A, B false, B, A false, that's a tie. I know it's a tie because neither of them come strictly before the other. So we have just as much power, but we might have to call the comparator twice to identify that tie if we want to. A lot of times we'll just break ties arbitrarily. So if it returns true, we do one thing. If it returns false, we do another thing. And that is what our code today is going to do, because often we actually don't care about ties. But we do have just as much power as the int version, and we have simpler code to implement, which means I can focus on the more important stuff when I talk about all this stuff, like inheritance. Oh, this slide doesn't. I forgot this slide doesn't have inheritance. Next one, no. One of them will. Inheritance is coming. So we'll write our compare method. This takes two ints, and I want to sort ints in decreasing order just to show that we do have some extra power here. If you tell Java to sort an array list of integers, it's going to sort in increasing order because it's using the default comparator, and the default comparator is the less than operator. I'm going to switch that to the greater than operator, and that's going to sort my integers in decreasing order. Now, we can sort these things in any way we want, anything we can imagine, but this is the easiest, simplest example to use for a lecture, while still showing that we have custom sorting here. And with this object, we've talked about the default constructor before, and we have a non-static method, so we need an object of this type in order to call the method, but we don't have a constructor. We've talked about default constructor before. This used to be the first time it'd come up in class, so I had this cheeky little line here. But we know that that's going to give us the default constructor, just because it came up in lecture a few times naturally this semester. We have the default constructor. So writing this default constructor in our class takes no parameters and has no code in the body, is the same exact thing as if we don't write it. So this is the constructor we get by default if we don't write any constructor. So these two classes are identical. That's the constructor we get. So we do still have a constructor. We can say new int decreasing and still create objects of this type. The constructor just doesn't do anything. And we are using inheritance. It's inheritance week. We better be using some inheritance. So here we go. We're going to use inheritance. We have this comparator class. This class is actually in your homework handout. It's been in the data structures package from task 1. When you first cloned the repo, it's been sitting there just waiting for some action on task 4. This is where the comparator is going to come into play. Towards the end of task 4, you'll extend that a couple of times. The comparator is going to take a type parameter t, so we can compare any type, and have a compare method that compares two values of that type. We're going to write some default behavior for the compare method. I'm going to just return false here, but we need something just so this code can compile, just so we don't get errors. We need to have it return something. Since it's supposed to return a Boolean, it better return a Boolean. Well, yeah.
So when it goes to the code, does it go to the override compare method or the compare method at the top?
If it's of type int decreasing, yes. Let's see.
But if it's a type integer, then it goes to the bottom?
If we create an object of type int decreasing, we get this compare method. Right? But we could technically say new comparator, and then it'll just always return false because it'll get that method. But we're going to create new int decreasing and get the second one. So our int, we have a type parameter, and we have to resolve this type parameter somehow. And we're going to, or generic, I'll try to use the word generic since we're in Java. And we have a new way of doing that here that we haven't quite seen before. It's the same idea. We have a type, a generic type, and we need a concrete specific type. We need a type argument to give to this generic type. And we can do that right in the extension line. We can extend comparator, and instead of extending comparator of t and giving int decreasing a type parameter, since this type, when we're writing this class, it's explicitly designed to compare ints. It's an int decreasing comparator. It's specifically made to compare ints. We're going to specify the type parameter right here. Extends comparator, and then say this is what t is going to be for this class. Extend comparator of integer. And now when we write our compare method, we have to write compare of t. Well, t now is integer inside the int decreasing class, so I have to write a compare of integer right here. And since this is a generic type, I can't use int anymore. I'm forced to use capital I integer. So that's the reason why we're switching to capital I integer, because we have the type parameter. And then I'm going to override that compare method to actually do what I want to do. So override compare of tt. T is integer, so compare integer. That's going to give me my override, and then that's where we're putting our greater than operator. This came up in the other lecture, so I'll mention it here too. There is no, this method should always be overridden. Return false, I just have there, so this code will compile. When we do get to polymorphism week, we're going to expand this. We're actually going to revisit our comparator and change it into an interface. We're going to make this an abstract method, which means we delete the body of the method, and we just cap this off with a semicolon to say there will be a method that exists called compare that returns a Boolean and takes two values of type t, but this class won't implement it. To do that, we either need this to be an abstract class or an interface, and that stuff we'll talk about in polymorphism week. Since we only have classes right now, every method must have a definition. We can't have abstract methods yet, so we do have to give some default implementation, even though this compare method is designed to be overridden by any child class. Because if we get a comparator that just always returns false, we're not getting the sorted order that we want. And since our comparators are classes, we have all of the power of classes. We can do a lot of stuff with this. We'll switch back to our int decreasing just to keep it simpler for the lecture, but we can make this as complex as we want. This can get really crazy really fast. If we want to sort different types in different ways, which is our goal right here, we want to sort any type using any comparator, so sort anything in any way. We want that full power, that full flexibility. Our comparators can get pretty complex to accommodate that. If I want to sort game items by their distance from the origin of the game, their distance from 0, 0, I'm going to extend comparator of game item, write my compare of two game items, and I can write a helper method. That's something we can do in classes. I'm going to write an extra method that's going to help me compute these things. And that's going to compute the distance of a game item from the origin. We didn't see the getters. I never showed those in the slides, but it's in the repo where a game item will have get x, get y, set y. And compute the distance from the origin, and then compare in increasing order based on the distance to that origin, increasing here because I have the less than operator. And we can take this a step further. If I want to give distance to origin a non-default constructor, maybe I want to give it a constructor which is going to take a reference to a player object and then sort, instead of the distance from the origin, the distance from that player. Sort all of my game items by their distance to a specific player. And maybe I want to do something with the closest item to the player. A lot of reasons why I might want to do that. Maybe the player's in reach of multiple game objects, and I want to know which ones are are in reach, and then out of those ones, which one is closest. Get the one at index 0, that's the one when the player hits interact, that's the one they're going to interact with, whatever one's closest. A lot of reasons we might do that, and with our comparators, we have that power. Yeah.
So if return distance A is less than return distance B, that means if the item is closer to zero than the A.
The other way around. So if distance of A is less than distance of B, that means A is closer to the origin than B. This distance method is computing distance to the origin. So if the distance to the origin of A is less than, then it's going to be closer to it. In the decreasing, I'm using the greater than operator. That's why we're getting the reverse order, the reverse thing. But the point here is, with classes, like there's no restriction to what we can do here with our comparators. It's a class. We can do all of our class stuff. Constructors, instance variables. Oh, with the constructor example I just said, we would store that player reference in an instance variable. Instance variables, constructors, extra methods, anything that we can do with classes, we can do with these things, as long as we do have a compare method, which actually, even in this case, we do inherit this one. We always have a compare method that always returns false, but we probably want to override it with new behavior, but we can add that to whatever else this class does, which should all be related to comparing things. But we can have a lot of helper methods, helper instance variables, a lot of stuff to accommodate that. Okay, so we can compare two values. Go us, good job, right? But how do we use this to actually sort? I got an array list of 1 million elements, and I want to sort them. And the tool that I'm giving is a comparator that can compare two things. What do I do? And the short answer is we're going to call the comparator a whole bunch of times. But let's see exactly how to do that with insertion sort. In 115, I think they either go over insertion sort or selection sort, and I think some semesters they switch between them. They both serve the same purpose, the same educational value in the course. So I don't know, I don't remember which one they're on when you all would have taken the course. But if you haven't seen insertion sort, it's not too complicated. We're going to see it right now. With insertion sort, what we're going to do is create an output list. So this is the list we need to sort. We're going to create an output list, which is going to initially be empty, and then we're going to iterate through the input values. Every value, we're going to ask a question. Where should this one go in the output? Where should this one go in the output, and where should this one go in the output? And then copy them into those locations, and then we'll have output being the fully sorted list. With the first value, there's no decision to be made. The output's empty. There's only one place to put it. It's got to go in index 0. No other choices. Easy day, easy decision. When we get to the next one, this is where our comparator is going to start doing some work. When we get to 6, we have to decide. At this point, the output is just the value 1. We get to 6, and we have to decide where 6 is going to go. We're going to invoke our comparator, and we'll say, hey, comparator, and we have to pick what order we're going to put the arguments in. I chose the value from the output first. We're going to say, comparator, does 1 come before 6? And that comparator is going to say, hell no. No, it doesn't. Now remember, we're sorting in decreasing order, so 1 is not coming before 6. We don't know if it's a tie. I mean, obviously we know, but the comparator is not going to tell us if it's a tie or not. It's just going to say no, doesn't. And at that point, we know that 6 is going to go at index 1, and we're going to slide 1 down the list. When we get to 5, we're going to invoke our comparator a few times. We're going to say, hey, comparator, does 6 come before 5? It's going to say yes, or return true. Does 1 come before 5? It's going to say false. It's either a tie or 5 does not come after 1. So we're going to insert 5 right here. And what we're doing here, and what the code's going to do that we're going to see on the next slide, is going through the output. Either a few ways to do this. Actually, let me start with what the code doesn't do. We're going to go through the output and keep asking the comparator, does this come before the value I'm going to insert? And as soon as that comparator says false, we know we found the location where we're going to insert that value. What the code is going to do is go through the entire output and count the number of times that the comparator returns true, that count is exactly the index where we're going to insert. Yeah. Yeah. Asymptotically, it ends up being the same here because the algorithm's so bad anyway. But yeah, this can be made better with a linked list. Kind of. Well, it's going to be bad no matter what we do, but we could use Bogosort to get worse. Yeah, it's not the worst sorting algorithm, but it's pretty bad. The problem with the linked list is it's going to take O of n time to find where to insert. This we could actually find where to insert faster by changing this to a binary search and get this going pretty quick. But then, as you say, the inserts are still going to take O of n. So we can't get out of O of n squared anyway. If anybody doesn't know what we're talking about here, don't worry. 250 is going to tell you all about everything that we just said in great, great detail. All right, so here's our insertion sort code. I always get insertion sort and selection sort mixed up. It's easy when it's on my slide, but yeah. Insertion sort, you're choosing where to insert. Our insertion sort code, so let's look through this. It's quite a bit of code, but I'll maintain that this code isn't too complicated. I think every one of you should be able to go through this and figure out what it's doing if I just left it to you to figure that out. But it'd probably take you, a hot minute or two to parse through all of this and really figure out what it's doing. So let's go through it, and I want to highlight especially the kind of new stuff that we're seeing. What we have is the feature that we want when we write this sort method. I'm going to put it in a sorting class that takes a type parameter so I can sort any type. I'm going to create a sorter of a specific type and take a comparator of that type in its constructor. So I can sort any type, any Java type, using any comparator, which gives me the full power to sort anything in any way. And we write this sorting method, this actual sorting method, we write one single time ever. And that's exactly what I want. I don't want to write my sorting method for every type of thing, for every way. I don't want to write a brand new sorting method when I want to sort by distance to a player instead of distance to the origin. I don't want to write another one for decreasing ints. I don't want to write another one for sorting ints by their absolute values. I don't want to do that. I want to write one sorting method one time. And this is what the Java devs did, or the developers for any language. They're going to write one sorting method, and that's it. And then you can sort anything, any class that you came up with that the Java devs had no way of ever knowing would exist. You can sort those things. Just give it a data structure of those things and a comparator to tell it how to sort those things, how to compare two of those things. And the sorting algorithm will take it from there. It'll do all the rest. That's what we want, and that's what we got here. Everything's totally generic. Generic type, generic comparator that's going to compare in some way. And our method actually doesn't care what this comparator is doing, how it's comparing, as long as it compares consistently, hopefully. But even if not, that's the caller of our method's problem to deal with. Our sort method itself is going to take an array list of that type and then create a new output. This is what we saw in the diagram, a new empty array list for the output that we're going to insert into. And when we create, actually I want to go back to this one. When we create this sorter, we're going to specify what t is and then give it a comparator that compares two values of type t. So our type parameters, our generics have to match. Our comparator takes a generic, our sorter takes a generic. That generic should be the same for both of them. Whenever we have a reference, this is more review, but we have a reference to an array list that we're given, and we want to be careful what we do with this reference. We might not want to go over to the heap and make changes to this array list because those changes will take place on the heap. So over here in the main method, they'll see those changes after our sorting method is called. So we want to be careful or not. Some sorting methods, like Java's built-in collections.sort, is going to sort in place. So it's going to take that reference to your array list and actually manipulate the heap and actually sort your array list instead of creating a new array list and returning a new array list that is in sorted order with the same values. So sometimes you want to take advantage of that reference. Sometimes you don't. When you're writing your code, when you're designing your projects, deciding which one you want is a very important decision to be made. Ours is going to not modify the input. Java sorting does modify the input. And then our sorting method itself. We're going to iterate through each value in the input and decide where it's going to go. We're going to, by default, insert it at location 0. We're going to iterate over all the values in the output and ask our comparator, does the value that I'm looking at from the output come before the value that I'm inserting? If it does, we're bumping up that index by 1. So we're effectively counting the number of values in the output that come before the value we're inserting, and that count is exactly the index where we want to insert the new value. So if 0 elements in the output list come before the value I'm inserting that thing at index 0. And we're giving our add method a second parameter, which is actually the first parameter. Add method can optionally, it is overloaded to take 2 arguments. If you give it an int and then the value you want to insert, that's going to insert this value at this index. So instead of always adding at the next available index, if you want more control about where those values are inserted, you can call add and give it that index that you want to insert into. An O of 1 BOGO sort. If you can write that, go for it.
Technically, best case.
But best cases, but big O is worst case. You won't get big O of 1.
Is it omega?
You can get big omega of 1, yeah. Yeah.
What is like a BOGO sort? And like
It's
well,
it's
besides like a Pokemon reference, like is it something equally?
it is. It's a very, very inefficient sorting algorithm. I believe, I might be mixing up with another one, but I believe it's the one where you randomize the order of the list and check if it's sorted. If it is, you're done. If it's not, you randomize it again, you shuffle the list, check if it's sorted by taking your comparator, each pair of elements sequentially. If it's sorted, you're done. If it's not, shuffle it again.
Why would we want to do that?
You don't. Never do that. Never. But technically, it can be efficient because you might just be right on the first try. So, actually, is that even O of 1? Because you still got to take the time to shuffle it. It's still O of n.
I mean, you give it a shuffle list, right? So it can just like take the shuffle list, randomize it, and there's a chance that it'll just give you a sorted list right there.
Where's the complexity
Although
of
very
the
less,
sort-
probably.
shuffling?
Yeah. Just don't use it. I don't want to think about BOGO sort anymore. Don't use it though. Yeah, it's basically gambling. Gambling with your runtime and CPU.
It says
Alright.
O of infinity. It's the official.
Yeah. Oh, yeah. Because it might never get there. And I mean, the only good use of BOGO sort is if you want to use your laptop as a heater. It's really good at that.
What happens if you got like multiple BOGO sorts still?
No.
Like, does it like?
Moving on. We're moving on. Not talking about BOGO sort. Never use BOGO sort unless you're doing just purposely something really, really ridiculous. All right, so we have one potential problem here. I have a constructor that takes a reference to a comparator, and I'm giving it a reference to an int object of type int decreasing. But Java is strongly typed. The type of the argument has to match the type of the parameter. This variable can only store a comparator of t, and I'm giving it an int decreasing. What the hell? Why are we doing this? How are we doing this? Is this even allowed? And yeah, it is allowed. We can do this. This is actually perfectly valid, perfectly legal thing to do. Even though the types don't match, we're still good. But why? Why is this the case? The short answer is because int decreasing extends comparator. So since int decreasing extends comparator, it inherits from a comparator, it actually is a comparator. And we can treat it as a comparator because it's going to have everything that a comparator has. This is something called polymorphism. We have a whole week on it later in the course, so I'll leave the much longer explanation for that week. But for now, suffice it to say, this is allowed. This is allowed as long as it's part of the inheritance chain. As long as somewhere int decreasing extends comparator, we get away with this. Very powerful topic. Polymorphism. But yeah, for now, it's allowed. We can do it. We're allowed to. All right, memory diagram. Let's memory diagram this thing. And talk about all this stuff. And with this one, I'll say that there's not really anything new. I'll highlight the things that we haven't seen explicitly before. But we're getting to a point in the course. Actually, I think we're at that point in the course. Maybe a little bit in polymorphism we got to think about. Actually, not really. But we're at the point in the course where we're not going to see anything new in memory diagrams. Like, you know everything you need to do with memory diagrams. You could do, theoretically, you should be able to do quiz 2 and quiz 3 today. You would be able to do them even without understanding the concepts that we're going to cover, because the memory diagrams are going to no longer add new concepts. It's constructors, it's stack frames, it's references, it's all that stuff, code blocks. But we're going to combine those things in different ways. So you're going to see different ways of combining the things we already know. So the complexity is going to increase, but it's nothing actually brand new. If you understand everything about memory diagrams up until this point, you would be able to go through this memory diagram and go through the whole thing just fine. Same with trees. Trees behave on the heap and the stack a lot like linked lists. It's a node-based data structure. You have objects for the nodes in memory and references to those nodes, and those nodes have references to other nodes. It's the same idea for trees. And I guess polymorphism, trees and polymorphism are the only two topics we have left, ain't it? Is that true? Also graphs, but graphs is task only. It's not quiz or interview. Yeah, only 2 more quiz topics that we even have to talk about. Wow, the semester flies. It's only week 6. How is that true? Anyway, let's go through this thing. We have a case here. We have 2 method calls. They happen to both be constructors even on the same line. So we have to think about this a little bit. I probably, let me just say, I wouldn't do this on the quiz, but having an extra line here meant I had to make the font smaller or really cram everything in. So let's talk about this. Having a method call take another method call I might do on a quiz, but probably not with constructors. I think that's a bridge too far for a quiz. But it's not too complicated. We'll see it right now. Just not something I'd feel the need to do. We need to decide which one is going to resolve first. Which stack frame do we put on the stack first? And the answer is going to be we always have to bless you. We always have to resolve the arguments before calling a method. So before calling the sorter constructor, we need to know what its arguments are. We need to resolve this down to a value, which is going to be a reference. We need to resolve that down to a value before we can actually call the thing. And if you don't want to think in computer science terms, you can even just think in math terms. Whatever's inside the parentheses, you have to evaluate first. So we're going to evaluate inside the parentheses first, resolve the argument before calling a method. And we're going to call the int decreasing constructor. And here's where it's not necessarily new, but it's a new combination of things that we haven't seen explicitly before. Int decreasing has no explicit constructor, so it has the default constructor, but importantly, it does have a constructor. It has the default constructor, and it goes on the stack. We create that on the stack. We create our int decreasing object. Int decreasing has no instance variables. Comparator has no instance variables. So we have an object with no instance variables, but we do still get an object on the heap in this. And I forget if it came up in this lecture or the other lecture of couldn't compare be be static? And yeah, it could, but then it messes up our comparator here. It messes up this stuff if it's static. So it's weird having an object with no instance variables, but so we can pass references to these objects that have comparators of different comparators does help us out a little. So we have no instance variables. The default constructor is called, and remember, the superclass constructor is always called. Always, always, always. So even though int decreasing has the default constructor and comparator has the default constructor in int decreasing will still implicitly have that super and then parentheses. Remember, if it's a superclass, if it's a constructor call that takes no parameters, that super call is optional as well. So we have a default constructor that has no code in the body, but it implicitly has super, open paren, close paren, semicolon inside of it, even though it doesn't actually exist explicitly in any way. So the comparator constructor, default constructor, is still called. So int decreasing and comparator, these two constructors, do both go on the stack, even though they're both the default constructor. Oh, I did this in the last section too. I got way ahead of my slides on this one. There's no return arrow in our memory diagram. Where would int decreasing, where would this return to? It's just returning into a method call. So no return arrow here. If it's not being stored in a variable, we don't draw the return arrow. There's no need to. So no return arrow. And then once that finally resolves, then we can finally call the sorter constructor, which is going to have a return arrow because it's stored in sorter. So we'll call this method, create a sorter object, give it a random reference number. I was feeling 321 when I made this slide. And this constructor call resolved to a reference to the object that was created, OX350. So comparator gets the value OX350. That's going to be assigned to the instance variable comparator. So we get OX350 as the comparator in this sorter. Create a new array list. Now the calls that are internal to Java we don't care about in our memory diagrams. The ArrayList constructor, the asList static method in the arrays class, we don't care about either of those, even though there would technically be 2 more stack frames put on the stack. Internal to Java, don't worry about it. Put list as a reference to that array list that's created with the values 165. Now we're ready to call our sort method. Finally, we get to sorter.sort. Sorter.sort, we're calling it from the sorter, an object of type sorter. So we'll look in sorter, we find sort. This is OX321. And input is list, which is OX654, a reference to this array list. Again, ArrayList constructor, we don't worry about on the stack. It's internal to Java, but output gets a reference to a brand new empty array list. And then we're ready for our loop. We're ready to start actually sorting. So for value to insert in input, we're going to iterate over the values of the input array. Input is 654. So the first value is 1. Value to insert inside the code block is going to get 1. Location, a variable is declared inside this code block, so that also goes inside the dash box for the for loop. Location gets the value 0. We're going to iterate over all of the values in the output. We create a new loop where value to compare iterates over all the values of the output. Well, guess what? There are none. So this loop doesn't execute not even a single time for this iteration of the loop. Location is 0. Value to insert is 1. So we're going to insert the value 1 at index 0 in the output array. And move on to the next value in the input. We just processed 1. Now it's time to process 6. Value to insert gets the value 6. Location is redeclared to 0. This is another one of them caveats where we do it a little different in the memory diagrams, where this is actually technically creating a new variable named location. So this variable named location is removed from memory, and then a new variable also named location is created in memory. To keep things a little simple, we treat this as a reassignment of the same variable in the memory diagram. So we're going to cross out the old value and write in the new value, because that's the way our code is going to behave. That's the way it feels still, but it is technically a new variable. But that doesn't really matter to us that it's a new variable. The point is, the end result is a variable named location that has the value 0, and our memory diagrams will get pretty cluttered if we create a new variable each time that happened. And even though the value isn't changing, we do still cross out the old value and write in the new one to show that there was a reassignment, and in this case, a full redeclaration of this variable. We'll still cross out the value. Okay, and then we iterate over value to over the output again. This time we actually do something. So we get an inner loop. So we get an inner loop. Code blocks do go inside other code blocks. Code blocks do go inside stack frames. We can nest these as much as we want. We could have a loop, inside an if, inside a loop, inside another, inside the else of a conditional. These can be nested as much as possible, as much as we want. So in this loop, value to compare is part of this inner loop. It's going to iterate over the values of the output. The value, there's only one value, it's 1. And then we're going to call our comparator. This.comparator.compare. This is called from the sort method, from the sort stack frame. This